Hello, everyone, and welcome to week 4 in artificial intelligence. Hopefully, everyone is doing well, and we'll jump right in because we got a lot to do today. We're going to talk a bit about logical agents, first order logic, and inference in first order logic. But first, we'll start with a discussion of the assignments. So, jumping straight into the assignments. We're between obviously weeks 3 and 5, as this is week 4. Keeping in mind that next week you'll want to be thinking about knowledge representation as your paper. So you might want to be starting on your research now rather than later. This week's discussion is to discuss knowledge representation. So why is it critical in AI? Defend your answer with citations or examples or some sort of logical sort of argument. Then, as always, some useful resources for this course. You might want to spend some time poking around there. Some pretty good stuff, including some Jupyter notebooks that have pretty good examples of all the stuff we talk about. So jumping straight into chapter 7, we're going to talk about logical agents. We'll start with a discussion about kind of why do they exist? Why do we need them? And the reality is that you have sometimes a reflex agent can do things like find its way through blind luck from one location to another. A chess program might calculate legal moves, but if it doesn't know the rules of the game, it may not know that a piece can't be on two different squares at the same time. So these are kind of logical constructs. And logic, in this case, knowledge-based agents, combine general knowledge with the current precepts, the things that it knows about its environment, to infer hidden aspects of the current state prior to selecting action. So they make decisions in a way based upon what they know, plus what they are seeing, so to speak, or sensing. So hence the precept. Drilling in a little bit about knowledge-based agents. So start with what's a knowledge base, right? So it's a set of essentially sentences, and sentences here doesn't mean like English sentences. It's a way of representing knowledge in a certain sort of format, in a certain language, right? So that's what it is. Sentences represented in a knowledge representational language, and represents assertions about the world. So they're essentially a set of rules that control what if something is true or not based upon some other things. So an inference rule, when one asks a question, and ask is an all uppercase because it's like an action of the KB, so of the knowledge base, the answer should follow, meaning that it can be inferred from what it has previously been told. And I'm not misspeaking. Tell again is another action on this world. So basically, what that means is that there's a rule that says, hey, here's some facts I know about the world. I can figure out some stuff using some rules based upon those things I know. So you can essentially derive new meaning. So a generic knowledge-based agent has this concept of tells, asks, and actions. So basically, you tell it what it currently is perceiving, ask it what it should do, and then tell probably what you did, and then iterate. So continue. Um, so the abilities of a knowledge-based agent. So an agent must be able to do these. They're a list of things that it should be able to do. Represent states and actions. So it needs to know how to represent state action. Incorporate new precepts. So it's got to be able to take stuff that it sees and then store it in some fashion. Update internal representations of the world because the world could change, or an initial assumption about the world could have been incorrect. And then deduce hidden properties of the world so that new knowledge is learned from those things which it is figuring out. And then figure out what's the appropriate action to do based upon the current understanding of the state of the world, and the things that are recommended based upon what it knows. And moving to a description level, the knowledge base agent is like agents with internal state. It can be described to different levels. There's a knowledge level of what they know regardless of the actual implementation, so it's essentially a declarative sort of language. Implementation level, which is around data structures and knowledge base algorithms that manipulate them, things like propositional logic and resolution. We'll talk about those later in this discussion. So there we've kind of done a little bit of an introduction of what is a logic agent. Now we're going to drill in a little bit into the Wumpus world. The Wumpus world, for those who are not initiated, is where you hunt the Wumpus, and the Wumpus is this monster. And the characteristics of the world are kind of interesting. And this came about from, and it even says there it was originally created in 1972. It was a text-based game back then. There was essentially a grid. Uh, it became a grid, then it was a dodecahedron. Um, and there was essentially a set of rooms that you moved between in one of the directions. And when you enter the room, it tells you something about it. So you could read about it if you want to go to this page, and you can actually play a game of Hunt the Wumpus. It's surprisingly challenging at times. So there are basically three hazards. You got a bottomless pit. So whenever you're near it, you know that there's a breeze. There's some bats in here that'll pick you up and drop you into random locations. However, the Wumpus is heavy, so the bats can't move him around or her. Um, and there is a fearsome, hungry, and unbathed Wumpus. You smell it when you get near it. The Wumpus has a bunch of suckers around it, so it won't fall into the bottomless pit, which is some of the hazards you have to avoid. And you kill the Wumpus by shooting an arrow at it. And if you miss, the Wumpus may move. These are variations on the game. It depends on the implementation. And sometimes you'll find stuff as you're wandering through this world of either arrows or gold, and you need to pick them up. So that's kind of the Wumpus world at a kind of high level. Here's a bit more of a detailed kind of explanation of what it might be. Again, you have squares when you're next to the Wumpus. You can smell them because there's a stench. You get breezes when you're near the pit. You can only move left to right or up or down, no diagonal movements. So that's why you don't necessarily know that there's a breeze uh, at a diagonal to a pit. And again, there may be variations on the game depending upon which ones you play. You'll be told that there is gold whenever you're in a square that has gold. But and this some implementations you actually have to say that you want to grab the gold or grab an arrow if they happen to be there. Generally speaking, the player's location is assigned at random at the start of the game. They start somewhere, and then they start working their way through the world. And it's about inferring that but when you're near something with a breeze, one of the four squares around it is a pit, right? And there may be multiple pits in the environment. And your actuators here is you go left, you go right, you go forward, you go down, right? So or up. And your sensors, breeze, glitter, smell. And that's kind of this world that we'll be looking at for just a little bit. So what are the characteristics of the world? Observable? No, you can only see what's local. You can't see the entire world. Deterministic? Yes. There's no randomness involved other than the initial designation of the world. Episodic? No, it's sequential at the level of actions. Static? Assuming the Wumpus doesn't move when you try to shoot at it, then yes, it's static. And certainly the pits don't move either. Discrete, yes. Single agent, yes. You can basically think of the Wumpus as a natural feature, not another agent. It doesn't move or have objectives. So representation of what the grid might look like and how we start keeping track of the environment, uh, assigning values to based upon the cell locations and so on. And again, more explanation of the various sort of things that you might know about the world as we move through it. And we start working through, okay, where the pits might be based upon some what we know about the world as we're exploring it. So you can start inferring, well, there must be uh, um, a pit nearby, and so on. So the same basic idea of around picking up gold and a few other things. So that's the Wumpus world in a high level. We will talk about that a little bit more later on, but part of the reason that was pretty popular was, first of all, it was kind of at the time a pretty cool game. People would go through and spend time actually playing it. Now it's at most kind of a trivial sort of thing, but it was kind of a logical sort of game that people would enjoy because it seems like you ought to be able to figure it out, but there is enough challenge to it that it's difficult. So moving into logic. So what is logic? First, formal language. There's a syntax. Expressions are legal, and when they're well formed, there is certain semantics about what a legal expression means. Uh, and so there's a we're not going to get into this into the depth that perhaps you might like, depending upon what your background is. Feel free to read these chapters closer than I'm going to cover the material because, well, we've got a lot of material, so I have to move pretty quickly. But it is similar in a way to arithmetic, um, but they're basically a series of expressions. You can think of them that way. Entailment is one thing follows another. So basically the entail sentence, alpha, if and only if alpha is true in worlds where KB is true. So that's what this is basically saying. So x plus 4 or x plus y equals 4 entails that 4 equals x plus y. So there's some other sort of things that go on here. Entailment is the relationship between sentences that is based on semantics. So that's entailment at a high level. Models are pervasive in logical terms. Logical models are, we think about the world that way. It's a structural representation of a world, and there's a formality to it. M is a model of sentences alpha if alpha is true in M. Capital M sub alpha is the set of all models of alpha. So there's some things in this thinking about a model of the Wumpus world, and there's a certain amount of kind of implication that goes on here. Um, and if you assume only pits, then you can start figuring out the possibilities of when you're in a cell with some breeze. A graphical representation of that, again, going over this pretty quickly. The key concepts here is that you do define a series of states in a way, but they're states of logical representation, and you refine them by adding additional knowledge. Logical inference is the notion of entailment can be used in logical inference. So the basic idea is that something follows something and lets you be able to have a couple of things and then they produce something else. Model checking is whenever you enumerate all possible models and check whether the alpha is true. So you're basically looking for internal consistency inside of the model. If an algorithm only derives entailed sentences, it is called sound or truth preserving. Otherwise, it just makes things up. So I is sound if whenever KB follows sub I alpha, it is also true that KB follows alpha. Completeness, the algorithm can derive any sentences that is entailed. So a complete whenever you can basically figure out the sentences that are necessary. Semantic perspective. If a KB is true in the real world, then any sentences alpha derived from KB by sound inference procedure is also true in the real world. So the basic idea there is that assuming you get your representations correct, if you can figure it out inside of a knowledge base, then it should have application in the real world, assuming that your representations are accurate, a reasonable sort of thing. Otherwise, what's the point of doing it, right? Because the reason we do models is because they're simpler than the real thing and easier to interact with. If it was just as difficult, then why would you use it? So again, I've went over chapter 7 there very quickly. Part of that is so that you guys aren't listening to me talk for hours. But do read it over. If you have any questions about chapter 7s or any of these chapters, let me know. That's my role here. Moving on to first order logic, and we may start off by returning to representation. So pros and cons of propositional logic. Uh, Propositional logic is declarative, and allows for partial, disjunctive, and negated information, unlike most data structures and databases. So that's definitely a positive. It's compositional, so meaning that you can derive meaning from based upon two different things. So um, whenever you see the little V, upside down V, that's basically, you can think of it as being an and. It's sort of like that. It behaves like that. It's actually an intersection, but it's close to the same sort of thing. Meaning is propositional logic is context independent, unlike natural language where meaning depends on context. So you can figure out what it means based upon simply what it says, not how it's used. Propositional logic is very limited expressive power, so not so good, because you have to basically be very precise whenever you're doing it. Pits cause breezes in adjacent squares. You can't really say that except by writing one sentence for each square. So you have to basically declare it at each one of those individual things. It's not a general term. First order logic. So whenever propositional logic is around facts, first order logic, like natural language, assumes the world contains objects, relations, and functions. So there's objects, people, houses, numbers, colors, wumpuses, whatever it might be. Relations, something, how they deal with each other, and functions that allow you to essentially kind of move from one to another. Logics in general. Um, the ontological commitment is what exists in the world. It's about truth. Epistemological commitment, what an agent believes about facts, is belief. So we separate out belief of the world versus facts of the world. Um, and so this is a bit of a kind of a table that breaks down the relationship between those things. Syntax and semantics of first order logic. And again, I'll probably skim over some of these things. So given some basic elements of first order logic, you have some constants. The examples here are pulling from history with basically some royalty. So you have some predicates, which is around relationships. So brother, functions, square root, leg of, and some variables, some connectives, some equality, and some quantifiers. Um, So you have this concept of an atomic sentence. It's something that can stand on its own, and it's made up of a predicate, which contains a series of terms. A term is a constant or a variable. So an example is basically brother, King John, and Richard the Lionheart. So is greater than the length of leg of Richard. So basically, this is saying that um, I'm not really sure exactly what that's saying. So it's basically a way of showing you some functions being used in a kind of almost recursive sort of way, or nested way, if not recursive. Complex sentences, they're made up of tonic sentences using connectives. So you have things of essentially intersections or ands and unions or ors and implication. And not signs. So the negation is the kind of upside down, this little kind of, I don't know what that is, turned on its flipped over and backwards else symbol, or whatever you want to call it. So basically what we're saying here is that there's some implication here and some two-way implications as well. And so this is about the expressiveness of that kind of language. Um, Truth in first order logic is sentences are true with respect to a model and an interpretation. Models contain domain elements and relationships between them. So interpretation specifies referments for. So you've got constant symbols and objects, you've got predicate symbols and relations, and functional symbols and functional relations. An atomic sentence predicate terms contains a bunch of terms, is true if and only if the objects referred to by term 1 through n are in the relation referred to by the predicate. So that's some rules around how those things work. A visual representation showing that apparently the left leg of Richard is greater than the left leg of the king. So not real sure. There's probably a story there that I'm not aware of around somebody's leg length. Models for first order logic, basically you can enumerate them given a vocabulary, and you can computing entailment by enumerating models. It's not going to be easy. So these things can get complex very quickly. Quantifiers, you have basically the two. There exists and for all are universal. They are what you would kind of think. There exists something that makes something happen, or for all something must be true. We'll talk a little bit about that here shortly. So a universal quantifier variables sentence. So everybody at some university is smart, is what this is implying. So the for exist universal x p is true. So that's basically saying for all x, p is true if in model M, if and only if p is true, where x being each possible object in the model. So roughly speaking, it's equivalent to the conjunction of instantiations of P. So you can kind of see the concept. Existence quantification basically means there's at least one in the set. So existence of XP is true in model M if and only if P is true, where X being some possible object in the model. So there exists at least one in the model. Properties of quantifiers. Um, Universal X and universal Y is the same as universal Y X, and so on. Existence, although it's not going to have that symmetry. Uh, and if you start thinking through those, they make some sense. Equality is true under a given interpretation if and only if term one and term two refer to the same object. So it's about equality of them being the same one, not necessarily about scale or size necessarily. So those sort of checks could be a little challenging at time. And whenever you're dealing with first order logic knowledge bases, returning to our WUMPUS world sort of scenario, you tell the knowledge base of precept, of smell, breeze, and so on for a given location, and ask for the best action at a certain time through the process. Using first order logic, um, these things actually do have application. Some of these are a little bit contrived, but whenever we take a look back at some of the early experiences we had with knowledge bases inside of artificial intelligence, it's very much about this first order logic sort of thing. You would a good example of this is medical interactions. So knowing the various types of things that can interact with each other used to be very challenging, but over the years they've developed basically a set of knowledge bases that know exactly how interactions are going to occur. And that's why whenever you go to a pharmacist and you get a prescription and you take other prescriptions, they're able to catch those ones which are going to cause you grief. And all that's being done because there's no they don't view it as being a probabilistic sort of experience. Instead, if you're taking medications A and B and you add medication C, then an interaction is likely to occur between one or more of those medicines. So they've got that stuff documented. So when we how did they get there is probably around this whole knowledge engineering and first order logic sort of thought. Whenever you're doing knowledge engineering, you start with identifying what the tasks. So what are you going to do with this knowledge that you're going to be representing in some fashion? You assemble the relevant knowledge. Basically, this is about going out and gathering it. In the case of the prescriptions, they spend a fair amount of time talking probably with the pharmacists or the pharmacological producers, so the manufacturing plants that are actually making this stuff. They probably also had captured as part of the experience instances where it happened for a large portion of the population, and so on. So once you've acquired that knowledge, you describe the vocabulary of how you're going to translate that knowledge from domain level knowledge into logic level names, so that you're mapping it so that it's something that can be represented inside of the knowledge base. Then you're going to determine the axioms of basically the general knowledge, encode the general knowledge around the domain. So you're going to put it into some way that can be captured, encode a description of the specific problem instance, pose queries to it, uh, and get answers. And then basically you're going to debug it to make sure it's really working correctly. So in summary, first order logic, it's about objects and relations and semantic primitives. You got some syntax with some constants, some functions, some predicates, qualities, and quantifiers. And it is increased in expressive power sufficient that it can define the Wumpus world for what that's worth. And with that, we wrap up chapter 8 and we move on to chapter 9, which is around inference and first order logic, which is kind of where it really gets interesting and kind of the point. You have to have these other foundational things so that you can actually do inference, which is what you really probably care about when we're talking about the realm of solving problems, right? So universal instantiation, some characteristics of that. So a king that is greedy is evil, right? And then you end up with some things that can end up being kind of deriving some additional information. So existential uh, existential instantiation. Basically, there exists an instance, right? For any sentence alpha, variable v, and constant k that does not appear elsewhere in the knowledge base. So there exists a crown on John's head. Continuing that logic, it can be applied to new sentences, and so you'll oftentimes, as part of this process with populating a knowledge base, there's an initial set of knowledge that goes into it, but as it operates, it learns more knowledge. Then you're going to do some reduction to propositional inference. And so this is basically attempting to simplify the logic or expand the logic to something that's more useful, and continuing that conversation around reduction. So there's some problems with the propositionalization. It generates a lot of irrelevant sentences, and uh, it may produce facts that are irrelevant, so they don't necessarily help. So it's not necessarily as directed as you might want. To unify uh, knows John X and knows Y Z, um, is the idea here is you're trying to basically combine them together in a way so that you can get something unique out of it. So here's an example of the unification algorithm. Again, these are high level concepts. Don't get hung up on the details. Understanding kind of what the point of logic representation is and where it's used, because the reality is that most of um, the work that's done in AI today is less about logic and knowledge representation and is about connectionist approaches, which we'll talk about later on. So an example of a knowledge base is the law says that it's a crime for an American to sell weapons to hostile nations. The country, Nano, an enemy of America, has some missiles, and all of its missiles were sold to it by Colonel West, who is an American, and prove that Colonel West is a criminal. And we do that by basically saying all Americans and weapons sales to a hostile country is a criminal. Namo has some missiles that it got from basically Colonel West. Missiles are weapons. An enemy of a country counts as hostile. So that's basically the representation that one would do to solve that problem. So whenever we have this representation of knowledge, we want to figure out ways of solving for certain values. One approach is to do it in a forward chaining approach. And this is basically taking everything that you know and essentially iterating through it until you don't generate any new facts. And that's essentially what this is an algorithm for basically expanding the knowledge base based upon what you know until you either reach your goal, or you don't find a solution, you exhaust the search space. So basically, when we talk about sound and complete for first order definitive or definite um, clauses, um, there are logical proofs that have proven this. Datalog was is a first order definition clauses and no functions. So it's basically was is a type of a database, and it doesn't necessarily terminate in certain situations. So there's times with forward chaining that you'll basically do it a certain number of times and then you stop. So incremental forward chaining, no need to match a rule, or iteration K if a premise wasn't added in iteration K minus one. So basically, it's a it's a way of essentially kind of stopping your way forward. Matching itself can be expensive. So basically, whenever you're looking and comparing things, matching can be expensive as far as computationally goes. And forward chaining is widely used in deductive databases, so you'll definitely see it in use. Um, and the a hard matching example using essentially that constraint problem we spoke about last week, and it is NP hard. Backward chaining is kind of, as the name would imply, results is it starts in a different way. Rather than starting with what you know, you start with what you want to know and you work your way backwards. So you start with the goal and you move towards your current state. It's essentially a depth first recursive search, and space is linear in size of proof, but it may be incomplete because of infinite loops. You may not find your way back all the way, and it may be inefficient because you may reach the same sub goals multiple times. You can address that by trading off some storage for speed. So you're going to take up more space, but it's going to be faster. And this is widely used in logic programming. Logic programming versus procedural programming. Logic programming, you identify the problem, you assemble information, you encode it in a knowledge base, you encode problem instances as facts, then you ask queries, and then you find false facts. Procedural programming, you identify the problem, assemble information, figure out a solution, program a solution, include problem instances as data, apply the program to data, and then debug for procedural errors. Logic programming has been around for quite some time, though again, it's not nearly as popular as it once was. The classic example of logic programming is Prolog. You might think Prolog is no longer around, but trust me, it is. I was doing some research in my dissertation around a complex event processing system, and it was implemented in Prolog. So in order to actually use it, you would have to go download and install Prolog, which you can still do. So interesting fact there. It did not go away. And this is showing kind of a representation of our previous criminal for selling weapons story in Prolog. And the idea of these sort of things is that you define your information as a series of kind of statements about the facts, and then it comes up with a solution, somewhat similar in nature to symbolic processing. Moving on to resolution. Going to go over this fairly quickly, but it's a way of a kind of, for lack of a better word, solving the problem. Um, and it's talking about converting things to a conjunctive normal form. Um, Again, it's good to know what this stuff is. You're probably not going to do it. But this is basically saying everybody loves animals, is loved by someone. So for all X, And for all y animal that is a y implies loves xy, implies everybody, there exists somebody y that loves xy or yx. So um, again, potentially you need to know it from a background to understand that logic representation is important, that knowledge representation is important, because with most things that execute, you need to have the knowledge in place, the data in place, so that you can do evaluations of it. So with that, we've completed a brief discussion of all 3 chapters this week. We'll close with questions. As always, if you have any questions, feel free to reach out to me, send me an email, text message, whatever it might be. I'll get back to you as soon as I can. Stay safe, and I'll speak with you next week.